Welcome to another class. Today we'll be talking about scalars and vectors. Okay, so quickly let's look at quantities and its classifications. So a quantity is any property of a material or system that can be quantified. That is, it can be measured. So whenever we have a property, okay, of a material that requires measurement, requires for us to quantify it, to find its magnitude, we call it quantity. An example of a quantity is length. Okay, that's a property of a material that we need to quantify. How long is this material? How wide is this material? All right, we have things like force, we have weight, we have mass. Okay, these are properties of a material that we need to quantify. We need to know its magnitude. You get? So when we have this kind of properties, we call them quantity. Okay, and they're usually classified in two ways. One as scalar quantities, and then also as vector quantities. Okay, so scalar quantities are quantities that needs only its magnitude to completely define it. Okay, once you know the magnitude, that quantity is completely defined. Right, and examples are volume, mass. We have them here: density, length, distance, speed. Okay, if you have the magnitude of any of these quantities, they will be completely defined. Right. Meanwhile, vector quantities are quantities that need the magnitude, but not just the magnitude. They also require the direction for them to be completely defined. So for scalar quantities, have that property, it's completely defined. When you come to force, you cannot define it only by its quantified property, the measured property. No, you have to also let us know what direction that force is being applied. So to completely define a vector, you need direction. So scalar quantities require only magnitude, vector quantities require magnitude on one hand and direction on the other hand to completely define them. Let's look at the addition of quantities. So if we have to add scalar quantities, okay, we simply add them by algebraic means. An example is we have two clocks and we want to put them in a box. We need to know what the box will likely weigh, so we need to know the masses of both clocks. So to get the masses of both clocks, we simply add both masses together. So we have the mass of one clock to be 0.9 kg and the mass of another clock to be 1 kg. So we simply add them together algebraically, okay, and we have 0.9 plus 1, which gives us 1.9 kilograms. All right, so the total mass of both of them would give us 1.9 kg. Now, what if we have to add vectors? All right, remember, vectors need to have their direction accounted for. So let's take an example. We have two people pulling on a box in the same direction. They apply forces Fa equal to 6 newtons and Fb equal to 10 newtons on the box. What is the resultant force on the box? So let's have a diagram to represent what we have just described from this question. So these are the two people pulling on this box, and one force is 6 newtons, all right, in this direction. The second force is 10 newtons in the same direction. What is the effective resultant on the box? What is the effective resultant of the forces on this box? Okay, so this question is same as asking what is the result, what is the effect of the result of these two forces on this box. So we can define the resultant vector as a simple vector which has the same effect in magnitude and direction as the original vectors acting together. So we have these two vectors, but the resultant vector is going to be just one vector. Okay, you can take out these two and represent these two with just one vector that would show us the effect of these two forces on this box. Okay, so if we have to find the resultant force, in this case, we're simply going to add both forces, all right, Fa plus Fb. Okay, since both of them are in the same direction, we have it to be 6 plus 10, which will be 16 newtons westward. Okay, we're adding westward, so we have a sense of the direction of the force. All right, we can also decide to take this direction as negative and take this direction as positive. Okay, with regard to, you know, the horizontal axis, this negative, this positive. So if we do minus 6 plus minus 10, we will now have minus 16 newtons. So that negative sign will make us know that it's in this direction. All right, okay, let's move on. So another example would be, what if these forces oppose themselves? So let's say we have two people pulling on a box in opposite directions. They apply forces Fa equal to 6 newtons and Fb 10 newtons on the box. What is the resultant force on the box? Okay, so this is the same question with the previous one, except for the fact that these two forces are now opposing themselves. Okay, so if you have this diagram depicting what is told here, we see Fa is in one direction, Fb is in another direction opposite to Fa. So how do we sum these forces together? Now, this will help us appreciate why vectors can't be properly defined with only magnitude. Because if you want to consider only the magnitude of these vectors, we would simply add 6 to 10 and we'll have 16 newtons. Same effect as we had with both forces acting in the same direction, which wouldn't be right, because if you're pulling this box 6 newtons to this side and 10 newtons to this side, the effective resultant or the effective result on this box will not be 16 newtons. This box will not experience 16 newtons in any of the directions. All right, so that will be wrong. Okay, so that is why we need to consider direction. All right, so if we take this to be our negative direction and this to be positive with respect to the horizontal axis, of course we'll have this as minus 6 and we'll have this as plus 10. So if we sum this together, we'll be having minus 6 plus 10 newtons, which would give us 4 newtons eastward. Now, the fact that we have positive here alone would make us know it's in this direction, but we can always add eastward to clarify that, yeah, for sure the resultant force will be in the direction of the east, okay, which is this way. So even if you have 10 newtons pulling this way and 6 newtons pulling this way, the effective result on this box will be 4 newtons moving this way. So this box will experience a 4 newtons force in this direction. All right, so the resultant force will be if I want to represent the resultant force here now, I can simply take out this force. I can simply take out this force, take out this one, and then just draw one line of force, okay, in this direction, and put 4 newtons there. And of course, that is the force this box will experience in this situation. So let's move on to the law of forces. When it comes to vectors, there are certain laws that help us analyze and help us solve problems. Okay, so the first of such laws we'll be looking at will be the triangle law of forces. Okay, now it states that if two forces acting at a point are represented in magnitude and direction by the two adjacent sides of a triangle taken in order, then the third side of the triangle represents the resultant of the forces in magnitude and direction taken in opposite order. Okay, so if I am to highlight key points from this conversation, I would say, okay, first of all, note that there are two forces, all right, acting at a point. Of course, acting at a point is very important to note, and these two forces are represented in magnitude and direction by two adjacent sides of a triangle taken in order. Very important, taken in order. Then the third side of the triangle represents the resultant of the forces of those two forces, both in magnitude and direction, taken in opposite order. So let's say we have force A and force B. Okay, so this is force A and this is force B acting at a point. So you can see that these forces are acting at this point here. Now, if these forces are represented in magnitude and direction by two adjacent sides of a triangle, so we can take this side and this side to be two adjacent sides of a triangle, but they have to be taken in order. This line is going this way, this line is going this way. This is one order. Okay, we don't have it like this. We don't have it like this. This is opposite order. Do you get? Okay, so we have them like this. So if they are taken in order, then the third side of the triangle represents the resultant of the forces in magnitude and direction taken in opposite order. So we are going to have our resultant to be the third part of the triangle taken in opposite order. So you see, it's opposite this one, in the sense that if we had all three sides to be in same order, we're going to be having something like this. Okay, so that's one side. This would be the second side. Okay, both of them are in order. Then we'll have the third side, which is the resultant, this way, but it's going to be in this direction. So this is all three sides of the triangle in order. But now they're saying that if these two forces acting at a point, which we took to be FA and FB, all right, these two sides acting at a point are represented in magnitude and direction by the two adjacent sides of a triangle. Fine, taken in order. So these two should be in order. Then the third one will represent the resultant taken in opposite order. So this one should be in opposite order, which means it's not supposed to be in this direction. Rather, it's supposed to be pointing this way. Okay, so this is opposite order. All right, so that's very important for us to understand. And then this configuration, this order, is usually called head to tail order. Head to tail. Okay, so the two forces should be head to tail. All right, so the second law is the parallelogram law of forces, and we have this to be: if two forces acting at a point are represented in magnitude and direction by the two adjacent sides of a parallelogram, then the resultant is represented in magnitude and direction by the diagonal passing through that point. So if we have two forces acting at a point, FA, FB, okay, and we decide to take these two sides as the adjacent sides of a parallelogram, then our resultant will be a diagonal that passes through that point. So this is diagonal of these lines, okay, passing through this point, the point of their action. So these are two ways we can find resultants of a vector. Okay, remember the first law. If you want to use that first law, it means you're trying to resolve your vectors into a triangle and to use the laws of triangles that we have available to solve your problem. If you're going to use this law, then it means you're trying to use a parallelogram to solve your problem, to get your resultants. And so this is just what you need to know, that once you have the two sides representing adjacent sides of the parallelogram, your resultant vector is the diagonal, all right, passing through that point. Okay, now these vectors don't have to be, this FA and FB don't have to be in order. All right, once you have them in this arrangement and you have your resultant, you can use laws of parallelogram to solve for a resultant. Okay, you can complete this as you can get this to be a complete parallelogram and use laws, certain laws like opposite angles are equal. Okay, some of the angles of the parallelogram will give you 360. You can apply all those laws to get your answer. Now for the triangle law of vectors, there are lots of laws that have to do with the triangle that you can use. You can use the Socrates law, the Pythagoras theorem. You can even use the cosine law and the sine rule, all right, for the triangle. Okay, so you have to decide which of the laws you want to use to solve your problems. Is it the triangle law or the parallelogram law. Let's remember that all these laws can be used to solve problems graphically, or we can use them to solve problems analytically. So we're going to try to do both, so we get to see how this can be done. All right, so first of all, let's try to solve an example. A bus moves from point A 100 meters eastward to point B and then moves 500 meters southwards to a point C. What is its resultant displacement? Okay, so let's try to get a free body diagram here. Okay, so the bus moves from point A, this is point A, 1000 meters eastward to point B and then moves 500 meters southward to a point C. What is its resultant displacement? Of course, we can see that these two sides, we can take these two sides to be adjacent sides of a triangle, all right? Because you can see it's even at right angle, they're both at right angle to themselves, so which means we can solve this problem with certain formulas available for solving right angle triangles. Okay, so for the triangle law, we can see that these two lines are already in order, right? All right, which means our resultant is going to be a line, the third part of this triangle, out of order. So we have our resultant to be dr. All right, so this is the line and it is out of order when compared to these other guys. These two are in order, this is out of order. Okay, so what do? We are looking for dr. We can simply apply Pythagoras theorem to solve this problem. Since both displacements are at right angles, we can solve this using Pythagoras theorem. So we know that Pythagoras theorem makes us understand that in a right angle triangle, the square of the hypotenuse side is equal to the sum of squares of the other two sides. So of course, this is our hypotenuse here. We know that AC squared, which is the hypotenuse squared, remember it says the square of the hypotenuse side is equal to AB squared plus BC squared. Alright, so if we bring in values here, we would have AB squared to be 1000 squared, BC squared to be 500 squared, which will give us 1250000. Alright, so we'll find the root of both sides, so we can eliminate the square above AC. So we have AC equal to 1118.034. Since we have gotten the magnitude of this vector, remember we can't define the vector only by magnitude, we have to define it also by its direction. So we need to know what direction the vector has. Finding the angle the resultant makes with this side. To find the direction of the resultant vector, we find the tangent of the angle theta, which is the ratio of the opposite side of the triangle to the adjacent side. Of course, we know from SOHCAHTOA that tan theta is opposite over adjacent. Alright, so if this is our triangle, our tan theta is BC, which is our opposite. We know this opposite is called opposite because it's opposite the angle we're working with. So opposite BC over adjacent AB. So this will give us 500 divided by 1000, which gives us 0.5. Alright, so if we make theta subject of formula, we have arc tan 0.5, which gives us 26.57 degrees. Okay, so therefore the resultant vector has its magnitude and direction to be 118.0 meters at 26.6 degrees approximately. Alright, so let's try to solve this problem graphically and see what our results will be, if we can get exactly the same results. Okay, so we're going to try to solve the same question graphically. Alright, okay, so we have the question: a bus moves from point A 1000 meters eastward to point B and then moves 500 meters southward to a point C. What is its resultant displacement? Okay, so the first thing we need to do is to understand that we have here we have a meter rule, okay, and it's calibrated in centimeters and in inches. All right, we have the inch here, we have centimeters here. Okay, but we can see that from the question the values we are given are in meters. We have 1000 meters and we have 500 meters. So we have to take a scale to get this drawing to fit on this paper. Okay, because if we are to draw 1,000 meters, of course we will need much more than the length of this paper to get that in drawing. Okay, but we can scale that down to something that can sit on this paper. So we're going to take a scale, we're going to be taking a scale of 100 meters to 1 centimeter. Okay, so if we do that, then 10 centimeters should equal 1,000 meters. All right, so let's note we're working with a scale of 100 1 cm to 100 meters. So now the question says that the bus moves from point A to point B 1,000 meters eastwards. So if 1 cm equals 100 meters, it means we're going to be having 10 cm. Okay, so let's draw a 10 cm line. All right, so that's about 10 cm. Okay, then it moves 500 meters southward to a point C. 500 meters southward. We need the help of another ruler here to get a perpendicular line. The line has to be perpendicular. So okay, so that's the man moving. Don't forget, of course, this is him moving eastward, and then this is him moving southwards. We know north is here, south is here, we have east and we have west. So this is him moving eastward and then moving southwards. So he moves southwards 500 meters. That should be 5 centimeters by our scale. All right, so we have 5 cm here. We mark out 5 cm there. So the question we're asked is, what is his resultant displacement? What is his resultant displacement? Okay, so of course, if you look at this, we can see that this is already arranged in a tail to head order. Okay, we have him moving this way in this direction, and then him moving down in this direction. So if you look at that, displacement is already in the tail to head order. Okay, so they're asking what is his resultant vector, and then we know from the law of forces that whenever we have two forces that can be represented with both sides of a triangle, then the third side of the triangle can actually represent the resultant of those two vectors. Okay, so in this case, this is our resultant vector, the red line. Okay, so this is how you can do this in scale drawing. So all we need to do now is measure the length of this to get our magnitude, and if we want to get the direction, we can measure the angle with our x-axis, but then we're asked to find the magnitude of this guy. Remember, we have here 10 cm, okay, and we have here 5 cm. Okay, this is representing 1,000 meters, and this is representing 500 meters. Okay, so let's see what we got here. If we check the length of this guy here, we have 11.2. Okay, so what we basically have is 11.2 cm as our value. Okay, and this, since we're using the scale of 1 cm to 100 meters, of course, we have 11.2 times 100, okay, which gives us the value in meters. So this is approximately 1120, okay, meters. So this is what we have. Okay, and if you look at the answer we got from the analytical problem we solved, we can see we had 1118, while here we have 1120. So remember, we approximated here, so it's about same value. Okay, it's about same value that we have for that. So you can see this is how we can solve this question graphically. So since we've already done this, let's also try to get the angle of this resultant, and that angle is this. Okay, that's the angle we're looking for. So let's read and see what we have. Okay, and see if it tallies with what we got analytically. All right, so we can see that we have this at the 26th mark here. Okay, this is 25, and then we have 26, so this is about 26 degrees. Okay, so theta is about 26 degrees. Okay, and if you check what we got analytically, we got 26.57, 26.6 approximately. So you can see we're on point. Okay, so that's how to solve this vector problems graphically. So let's solve another example. Two workers push a cart with a force perpendicular to each other. One pushes with a force of 10 newtons to the west and the other 12 newtons to the south. Determine the resultant of the forces applied. Okay, so if we draw a free body diagram, we can have something like this. So you see one worker pushes with a force of 10 newtons to the west. Okay, so this is in the direction of the west, and the other 12 newtons to the south. This is the direction of the south. Determine the resultant of the forces. Now if we bring out just the forces and make them form a triangle, because of course they look like two adjacent sides of a triangle. Okay, now looking at this, we can see that both forces are out of order. Okay, and if we want to apply the triangle law of forces, we know that they both have to be in order. So what we can do is to first rearrange the forces to have them in a tail to head configuration, so that of course they can be in order. And one of the things we could do is to, of course, we know that this is same thing as having a line here like this. Of course, we know we can have this as a complete rectangle, where this line can be represented in magnitude and direction by this one, and this one can be represented in magnitude and direction by this line. So if we decide to use this line here in place of this one, we would be right. Okay, so basically that's what we're going to do. We're going to have to use this line to replace this one. Okay, so we can have this both forces in order. Okay, so, or we can look at it as we are moving this line to this other side. We're sliding it along to this path and making this part now our point of action. Okay, it's same thing with here being the point of action, because if the point of action is here, this force is going to be pulling downwards at that point, and this force is pushing westward at that point. If we take that point to this side and make this the point of action, of course the force is still going to be pushing 12 newtons southward, and then this one is going to be pushing 10 newtons westward. Okay, which is same thing. So we move our force to this side, all right, which gives us same effect, but it can help us solve this problem using the triangle law of forces. Okay, so if this is the case, of course we know our resultant has to be the third line that completes the triangle, but in the opposite order. We can solve this using Pythagoras theorem. So we have AC squared, which is the hypotenuse, equal to AB squared plus BC squared. Okay, so this would give us 10 squared plus 12 squared, which is 244, we find the square root of both sides, and we have AC equal to 15.62 newtons. So we have to find the angle of the force, and we'll do that by finding tan theta, which would give us BC over AB. Of course, tan theta is opposite over adjacent. So tan theta will give us BC over AB, which is equal to 12 over 10, which gives us 1.2. So we make theta the subject of formula, and we have theta equal to arc tan 1.2, which gives us 50.2 degrees. So therefore, the resultant vector has its magnitude and direction to be approximately 15.6 newtons at 50.2 degrees south of west. So to understand why I wrote this like this and how this is usually pronounced, I think we need to take an example regarding that. So let's consider this diagram here with all these angles and try to see if we can state their angles, okay, in this format. Alright, so let's start with the 45 degrees. So we can see that this 45 degrees is between the north and the east. Okay, so when writing this like this, we write where we are starting from first, which is the north. So we're taking our measurements from the north heading to the east. So it's 45 degrees from the north. Alright, so we can write N where we're starting from, 45 degrees, and then east where we're headed. And when we want to pronounce this, we don't say not 45 degrees east. No, we say it to be 45 degrees east of north. Okay, so 45 degrees east of north. Alright, so let's look at the next one. We have the 40 degrees. So this 40 degrees is between south and east, and you see our measurements. We took our measurements from the south. Okay, so we write this as S40 degrees E. When we have to talk about it, we say it is 40 degrees east of south, 40 degrees east of south. So we have the 20 degrees vector here. If we want to talk about the direction, since we're taking a reading from the south and it's between the south and the west, we say it is 20 degrees west of south. Okay, and we write it as S20W, S20 degrees W. So we have the 60 degrees. All right, we see it's between the north and the west, and our reading is taken from the north. So we have 60 degrees west of north. Okay, and when we want to write it as north 60 west, N 60 degrees W. Okay, so apart from the Pythagoras theorem, we have the law of cosines, and we can also use this to calculate the magnitude of resultants. Alright, especially when the vectors aren't perpendicular. Okay, so if you have a situation like this, okay, and we have to find the resultant. Alright, we can see that these two forces, A and B, are not at right angles to themselves. So we can't use the Pythagoras theorem, because that theorem is basically for right angle triangles. Okay, and this is not a right angle triangle. We can't also use the SOHCAHTOA here, okay, because that is for right angle triangles, and this is not a right angle triangle. So we have the law of cosines, we have the sine rule that we can use for triangles like this that are not right angle triangles. Okay, so if we have two vectors that we want to represent as the adjacent sides of a triangle, okay, we can, and the triangle is not a right angle triangle, we can then do the same thing we've always done but use the law of cosines. Okay, so in this case we have to also make sure that both forces are in order. Okay, so we see that they are in order. Our resultant will now be the third part of the triangle that is in opposite order. Okay, now the cosine rule states that a rho squared is equal to a squared plus b squared minus 2ab cos theta. Okay, this arrow here is opposite this angle, so whatever you're taking as the side here has to be opposite this angle. So if you want to find b, let's say we want to find b, for example, I'm talking about the laws of cosine now. If we want to find b, it will be b squared equal to a squared plus r squared minus 2ab cos this angle, because it is opposite b. So that's how the law of cosine works. Alright, so we have r squared in this case, and we have cos theta. Okay, and that's because we are trying to find our resultant r. Now, this is the law of cosines, and we have to always make sure the two forces we're considering, the two forces we need to find the resultant for, are in order. Just in case you have two forces that are not in order, let's say we have an example. Let's say we have this as an example, okay, and these two forces are out of order with themselves, okay, and this is the angle between them. Now, normally you're supposed to make sure this is in order, and you solve with this formula. All right, so if it's out of order, you bring it to order, making sure you have it in the tail to head arrangement, and then you apply this formula and you get your answer. But for exams purposes, where you have to be very fast and you have these two forces acting out of order, unlike this one that is in order, and you have the angle between them, what you're supposed to do is to make sure these forces are in order by moving probably this one to this side, and then finding the angle, the new angle between them, all right, and using that angle as your theta, and then finding your resultant, which we'll do in the common examples. But then, just in case you don't have time, maybe for example it's a JAMB exam and speed is very important for you, okay, instead of going through that long process, we can take this angle here, all right, to find our answer. But when we're taking this angle, we have to change something about this formula, and that will be this sign. The sign will have to change from negative to positive. Okay, so we're going to be having r squared, all right, equal to a squared plus b squared. Now, plus here, instead of negative, we'll have plus 2ab, all right, cos theta. Okay, so this is what's important. Your plus changes. Okay, so this is the formula you now use here. You make sure you use plus instead of negative to use this angle here between these two forces. This is the actual way you solve the problem. You make sure they're in order and you apply the cosine rule. This is the cosine rule. This is not cosine rule. This is cosine rule. This is just a shortcut. Let's solve problems with this. So we have two forces of magnitude 8 newtons and 6 newtons acting on a table, and they act at an angle of 70 degrees between themselves. What is the resultant force? So let's get a free body diagram of what was described. So this is our table, and this is the 8 Newton force, this is the 6 Newton force, and we have 70 degrees, all right, between them. What is the resultant force? All right, so of course we have to put this in order, and that I have just done. Okay, so you see how it was before. I have just put it in order here now. So we now have the 6 newtons and 8 newtons in order. So we now have to find this angle. Okay, of course we know that this is our resultant now, which is the third. First of all, note that we're trying to use the triangle law of vectors to solve this problem. You can decide to use the parallelogram law of vectors to solve this problem. In that case, you know that what you're going to do is you have your two lines like this, your two vectors like this, okay, and this angle has been given to you, but then your resultant force is the diagonal that passes through this. You understand? We can now use the parallelogram law of forces to solve this problem, okay, by taking this to be adjacent sides of a parallelogram, okay, and then you can complete this as a parallelogram and solve this problem with laws of the parallelogram that we know. Okay, but now let's decide to solve this using the triangle law of vectors. All right, so in that case, this has to be in order, okay, which we have just done, and then our resultant becomes the third part of the triangle, the third side of the triangle, in opposite order. Okay, so what do we do? How do we get to find our new angle, which is theta here? Okay, so theta is 180 minus 70, which is 110. Okay, using the sum of angles in a straight line, because this, we had an angle here 70, which is the same as if we do this, if we elongate this line, if we come here and elongate this line like this angle here is that angle of 70 degrees that we had. Okay, remember this line was here, is the angle, this force here mixed with this other line. Okay, so you can see that this is our 6 Newton force coming down this way, these are 8 Newton force, this is the angle they both make with themselves, which is here 70 newtons. So this is a straight line, so angles on a straight line equal 180, so we subtract 180 from it, we have 110. So this place here becomes 110 while this is 70. Okay, but let's try to explain it further with this. So basically this is what we had before, 8 newtons pointing this way, 6 newtons this way, we had 70 degrees between them. Okay, so we moved this to this side so we can get it in order. So you can see that this is 70 degrees here. Okay, straight line, angle in the straight line equals 180, so we have theta plus 70 will give us 180, making theta 110. Okay, so you can even see that, of course, these are alternate angles here. This angle here is alternate this one, so we have 70 here, we have 70, and these are opposite angles, so this is 70. You can see it alternates. All right, so basically we have theta now to be 110. Okay, and then we're going to use theta now to find our resultant. But then when we need to find the angle of this resultant, the angle of the resultant, we will find alpha. Do we understand that? I believe that is understood. So we're using theta to find the resultant using the law of cosines, and then we'll now find the angle of the direction of the resultant, and that we'll do using alpha. So using the law of cosines, we have arrow squared equal to a squared plus b squared minus 2ab cos theta, which gives us 6 squared plus 8 squared minus 2 times 6 times 8 times cos 110, because theta is 110. Okay, so if we simplify that, we're going to get our root to be 11.5 newtons. Now, this brings us to the shortcut I talked about. Okay, to solve this problem using the shortcut, all we needed to have done would have been okay, we have arrow squared, okay, equals a squared plus b squared, all right, plus 2ab cos theta. Okay, now if we use this to solve this particular question just the way it is, you will see we'll get the same answer. So let's try. We're going to have our arrow to be the square root. Of course, let's assume we've squared this side, both sides already, so we have arrow. Our a squared is what? Our a squared will be, we can take our a squared to be 6 squared, or we can take it to be 8 squared, whichever one. So let's say 8 squared plus 6 squared, okay, plus 2 times 6 times 8, 2 times 6 times 8 will give us 96, so we have plus 96, all right, cos theta, which is 70 in this case. So we have cos 70. So of course we're finding the square root of everything. So if we solve this, obviously we're going to get arrow to be equals root, all right, 132.8. We're going to have it at 132.8. If we solve the root of 132.8, of course we're going to get this answer. So you see, it's actually a shortcut. We can just use this formula straight to solve these guys without putting it in order. Now this is if you have probably like an objective question and you don't have time to waste. But if you have if it's an exam where you have like to write down your steps, it's advisable you go through these steps. Put your forces in order, find the angle between them, and solve for your resultant normally. Alright, so let's move on to finding the direction of the resultant. So in this case, we're going to use the sine rule to solve this problem. Okay, so this is what we have. We have alpha here, we have theta here. We're going to use sine rule, and sine rule says b over sine alpha is equal to r over sine theta. So we have r over sine theta, we have b over sine alpha. We can also have a over whatever angle we have here, but we need to pick an arrangement that will give us one unknown. So here we know b as 8 newtons. Okay, we know r, okay, which we just found to be 11.5 newtons. Okay, we know sine theta, okay, which will be sine 110 because theta is 110. Okay, so what we're looking for is alpha. All right, if we bring in the values into the equation, of course we'll have 8 over sine alpha equal to 11.53 all over sine 110. All right, making sine alpha the subject of formula, we have this. Simplifying this, we'll have sine alpha to be 0.652. If we make alpha subject of formula, we have arc sine 0.652, which will give us 40.69. Right, so that's the direction of this resultant. Right, 40.69. So let's solve the same example using the parallelogram law of forces. Okay, so we have the same question, magnitude of 6.8 newtons acting on a table, and they have 70 degrees between them. So if you want to solve this using the parallelogram law of forces, of course we can represent this like this. Okay, we have 8 newtons, 6 newtons, and then the parallelogram law makes us understand that the resultant is a diagonal that passes through the point of action. Okay, so that's what we have here. Okay, so there are properties of a parallelogram we have to note to solve this problem. 1, opposite angles of a parallelogram are equal. All right. 2, all 4 angles sum up to 360. Okay, so we're going to apply that knowledge to solve this problem now. So if one angle is 70 degrees, the opposite angle will also be 70 degrees. Okay, so we have that here because remember from the first property, opposite angles are equal. So we have this place to be 70, which is here, to be 70, the angle between them. So automatically this side is 70 degrees. All right, and each of these remaining side will now be 360 minus 140 because 70 plus 70 is 140. So since all angles sum up to be 360, it means 360 minus 140 will give us the total of these two sides, which happens to be 220. So if we divide 220 by both sides, since they are equal, we would have 110. So that's what was done here. So each of these angles will become 110. All right, so if we have this now, we can now apply the law of cosines, okay, to solve this problem. So we have r squared equal to a squared plus b squared minus 2ab cos theta. Don't get confused with the shortcut. This is the actual formula for the law of cosines. It's not positive here, it's negative. Okay, so we can bring in our values. So this would give us 6 squared plus 8 squared minus 2 times 6 times 8 cos 110. If we simplify that, we're going to get 11.5 newtons. Okay, so the idea behind this was for us to get our cos 110. So to use this law of cosines right now, okay, we have to decide to take one side of this triangle. The law of cosines works for triangles, not for parallelogram. So we have to choose. Since we have two triangles here, if you look at it, this is one triangle, this is one triangle. So we can take either of the triangles, anyone we choose, to solve this problem. So let's say we take the triangle on the right. Okay, so we have 6 newtons here, we have 8 newtons here. Then we're looking for this line, the diagonal. Of course, we can do 6 squared plus 8 squared minus 2 times 6 times 8 times the angle opposite arrow, which is this. That's 110. So that way we can get arrow to be 11.5 newtons. So we go to find our direction, the direction of the resultant, and you see that it's exactly the same thing what we did before. We use sine rule to find the angle and we get our answer as 40.69. Let's go into resolution of vectors. Alright, so resolution of vectors is splitting that single vector you have. So let's say for example we have a resultant vector, right, and we want to split it into its component vectors. When you say component vectors, it means you want to find the vectors that make up that single vector. Alright, now if we're splitting it into its component vectors on the x and y axis, it means we are resolving the vector. Okay, that's what resolving the vector means. Okay, and previously what we've been doing is we've been trying to find the resultant of 2 or more vectors. All right, now in this case we have the resultant vector. We want to split it into its component vectors, and that's called resolution of vectors. Okay, so it's customary to resolve a vector into components along the x and y directions, which are perpendicular to each other, and these components are known as the rectangular components of the vector. So suppose we have a vector v as shown, okay, like this. This is vector v as shown in this diagram. The horizontal component, of course, of this vector v is vx, and the vertical component is vy. But then we can get the horizontal components as vx equal to v cos theta. Okay, this is the horizontal component. If you need to find it, all we need to do is to do v cos this, and we're going to find vx. Alright, if we need to find the vertical, what we need to do is v sin theta, and we get vy. So for the horizontal component of this vector, we do vx cos theta. So to get the vertical component of this vector, we do same v sin theta. Alright, the same angle to get vy. Okay, so let's take an example. A man pulls a mower with a force of 20 newtons at an angle of 60 degrees with a vertical direction. Determine the component of the force along the x and y axis. Okay, so let's say this is the mower and the man is pulling it at an angle of 60 degrees and is pulling with a force of 20 newtons. We are asked to resolve this his force into its component vectors. Alright, so if we have a free body diagram here, we have 20 newtons force, alright, at an angle of 60 to the vertical. Okay, now we're asked to find fx and to find fy. So remember we said fx is equal to f, in this case let's call this vector here f, so it's going to be f cos theta, and fy is f sin theta. So we need to find theta, which is the angle the force makes with the x-axis. Alright, so to do that we'll have to subtract 60 from 90 because this is a right angle triangle, so this complete angle here sums up to 90. So 90 minus 60 will give us theta as 30 degrees. So we can now find our horizontal component as f cos theta, which is 20 cos 30, which gives us 17.32. Then vertical component fy equal to f sin theta, which is 20 sin 30, which gives us 10 newtons. Now we're back to finding resultants. So to find the resultant of more than 2 vectors, we resolve each vector into its vertical and horizontal components and add all the horizontal components together and all the vertical components together. Okay, then we can now use the sum of these both components to solve for our resultant vector and to solve for the direction if we need to. Okay, so let's say we have a stone that has been acted on by 5 forces like this, arranged in this order. What is the resultant of the forces on this stone? In other words, what's the effective force this stone will feel? All these forces together, what is that one force that is equivalent to all these forces acting on this stone together? That's what we're about to find. Okay, so to do that, we have to find a horizontal component of all these forces. So we see for AX, right, for force A, which is 16 newtons, we find 16 cos 90. 90 in the sense we are using the angle this force makes to the x-axis. Don't forget, the force, the angle the force makes with the x-axis is what we're using to solve for all of them. So if you look at this force here, it makes an angle of 90 degrees to the x-axis. But then one thing we need to note is that it's on the negative y-axis. Okay, but then let's still try to find if it has a horizontal component. So we see the angle it makes with the x-axis is 90 degrees. So we can do AX equal to A cos 90, and A is 16 newtons. So we have 16 cos 90, which gives us 0. So you can see it has no effective force in the horizontal direction. The force of this A will be felt only in the vertical direction because it's not slanted in any way. So we go to B, we see B has a force of 15 newtons. Okay, if we need to find the component, the horizontal component of this 15 newtons, okay, it means we have to do 15 cos 60, because 60 is the angle it makes with the horizontal, okay, and it's on the positive x axis, so it's going to be positive. So 15 cos 60 would give us 7.5. So if we go to C, we see that C doesn't have any vertical component, it's just horizontal component. Okay, so it's 0 degrees to the horizontal. So our 10 newtons become Cx equal to 10 cos 0, which gives us 10. So it's 10 newtons in the horizontal. We go to solve for D. All right, D is 12 newtons. Okay, to find the horizontal component, 12 newtons cos 50, which gives us 7.71, is in the positive x direction. We go to find E for 20. Okay, so we use the angle 20 mixed with the horizontal, which is 90 minus 50, because if we add the angle 20 mixed with the horizontal to this 50 degrees, it's supposed to give us 90 degrees. So if we subtract 50 from 90, we're going to have 40 degrees. So we do 20 cos 40, but we have a minus sign because this 20 is on the negative x-axis. So that will give us minus 15.32. So if we sum this whole stuff up, that's 0 plus 7.5 plus 10 plus 7.71 plus minus 15.32. We're going to have a total sum of 9.89 for our horizontal component. Right, so we do the same thing for the vertical. We have A. To find AY, we do minus 16 sine 90. Minus because this is on the negative y-axis. Okay, so we have that to be minus 16. And of course, you know that we are taking sine 90 because the angle this guy makes with the x-axis, not y-axis. Both horizontal and vertical components, you're considering the angle it makes with the x-axis. That angle is 90 degrees. So we have minus 16 sine 90, which gives us minus 16. For B, we have minus 15 sine 60, which gives us minus 12.99. Negative because it's acting on the negative side of the y-axis. So coming to C, C doesn't have any y components, so we do 10 sine 0, which gives us 0. Okay, all right. D, we have 12 sine 50, which gives us 9.19. Is in the positive y-axis, so we have it as plus. Then we have the E, which is 20 sine 40, which gives us 12.86. If we sum this whole stuff up, we have minus 6.94. Okay, so to find our resultant, we find the root of the horizontal component squared plus the y component squared. So if we do that, it means we're going to be having 9.89 squared plus minus 694 squared. Right, if we simplify this, we're going to have 12.09. If we solve for this, we're going to have 12.09. So we have to find that. Even if we've gotten the resultant, we have to find the angle, the direction of that resultant. Okay, so we bring in our y component as minus 6.95, so is in this direction, negative y-axis, and we have 9.89 as the horizontal positive x-axis. So we have our resultant, okay, which is 12.09 here, the magnitude of 12.09. I want to find its direction. Okay, so we're considering alpha. Okay, so we can decide to just rearrange it as this. Okay, so we have rearranging it in the tail to head format. Okay, arranging it in order. So we bring our 6.95 to this side. All right, and of course we're going to be having it like this. Okay, so 6.95, 9.89. If we need to find this angle, of course we have a resultant. You can easily get tan alpha equal to y over x. Of course, tan is opposite of adjacent, so this is the opposite of the angle, which is 6.95, divided by the adjacent, which is 9.89. Do that, we have 0.703. Okay, so of course we don't bring in the sign here because the sign just goes to show us the direction of the y-axis, okay, which we have taken note of while drawing our lines here. So we have, if we divide this, we have 0.703. okay, we find the tan, the arctan of that to make alpha the subject of formula, and we have our angle to be 35.1. It means the force acting on that stone, the force that stone will experience is a force of magnitude 12.09 newtons, acting at a direction 35.1 degrees south of east. So our direction is 35.1 degrees south of east.